In an ironic twist, astronomers are exploring if terrestrial artificial intelligence can be used to detect potential extraterrestrial intelligence. A paper published in the scientific journal Nature by astronomers from the Search for Extraterrestrial Intelligence or SETI suggests that machine learning, a subset of AI, could be used to sift through thousands of terabytes of raw datasets from a million stars in the Milky Way. They believe AI could efficiently separate radio signals from potentially advanced alien civilizations from the blizzard of data accumulated as part of the Breakthrough Listen project to find intelligent life elsewhere in the universe. One of the astronomers involved in the Nature paper is Dr. Vishal Gajjar, a researcher working as a project scientist with the Breakthrough Listen program, as well as a staff astronomer attached to both SETI, and he got his PhD in physics in 2014 from the Tata Institute of Fundamental Research's National Center for Radio Astrophysics in Pune. Dr. Gajjar spoke to Mayank Chai Reports to explain how AI could help find radio signals from potentially advanced alien civilizations. Dr. Vishal Gajjar.
I was wondering from Botad in Gujarat
Mhm.
to a million stars. It must have been quite a journey. Tell me a bit about that.
Sure. I think I had interest in astronomy since I was very young. I guess like similar to everybody when they were like studying science, we had this one chapter in our science textbook about the universe, and I think that was the main reason why I got into it because uh, along with everything that the science was offering, this one topic about the universe kind of fascinated me. Like just thinking about how small we are. Like there are billions of stars in the galaxy, and there are billions of galaxy. We are insignificant in the face of the universe. That kind of just click something in my head that, oh, this is interesting and I would like to do something in this area. But like similar to many people of my generation, at that time I didn't know there were opportunities where one can do PhD and pursue astronomy as a career. So like many Indians, I did engineering, and then later I decided what I wanted to do with my life. With my life, so I did electronics and communication engineering. Fortunately, that field of electronics communication was very similar to what I am doing right now. So all the experience, like I am a radio astronomer. I'm not
Right.
like a typical astronomer that you might and think about. Like I don't use telescope to look through my
Indeed.
with my eyes. We use radio antennas basically, which are similar,
Yeah.
but it looks at a slightly different wavelength than what optical light does. So it is still relevant, but I did find my way through that, and I was able to get into a PhD program at TFR in at a center in Pune. I was a kind of a very enlightening experience for me to learn astronomy to take astronomy as a career, learn basics of it, and so yeah, I mean that sort of kept me going. But among all the different questions the astronomy is kind of meant to ask, I think there is one question which would probably going to be at the center of human interest since generation is going to be for next many generation as well till we find an answer to that. Is that are we alone in the universe? I mean that's the basic question that we have asked with science.
Right.
So similarly, I guess that's what motivated me, like, okay, if I want to do astronomy, what is the main question in astronomy that kind of will really push me to our current human knowledge? And that this is one of the questions that we have to make all the effort that we can in order to find the answer to this question. Are we truly alone in the universe? And through that, my interest, I think when I got an opportunity to come work at Berkeley, that was kind of a dream come true. There are not too many places at the time in across the globe, because this is a you can consider it as a blue sky science, because it's hard to really make sense about when do you actually make any significant discovery.
Indeed.
For any career astronomer, they don't really want to just report non-detections. Like you do want to see something, you want to see something and then say something about what you see. Um, the field that I work on is something where we are rare. We are still now we haven't really found anything. So because of that, the field is very, in a sense, it was very small. There were not many places where this kind of research was taking place, but I was kind of I was there at the right time when Breakthrough was announced. So
Right.
Breakthrough Listen is a program is actually the program to search one of the most comprehensive and detailed search for
Yeah.
what we call a techno signature, which is a sign of technologically advanced life, extraterrestrial life out there. It was launched at the same time when I came to Berkeley. I came before the program was launched, but then I became part of the program, and so far I've been part of that. Right recently, I've switched to SETI Institute, but I also work with Berkeley's Breakthrough Listen team. So yeah, I mean, through that, I think I am quite passionate about this question: Are we alone in the universe? And I'm quite hopeful that all the new effort that we are trying to make with the Breakthrough Program and the newer effort that we are trying to make with the SETI Institute, I think we are close to the answering that question. I hope within my lifetime, before I retire, I'll get to see something to be
You
quite
seem like a
extraordinary.
young man, so I'm sure you'll have something before you retire, at least. You know, I'm struck by the irony that we are now deploying terrestrial artificial intelligence
Uh-huh.
to help find potential extraterrestrial intelligence.
Yeah.
It's quite a flip. Talk to me a bit about that. To tell you the truth, I've been a lifelong science nerd. My background is physics.
Mm-hmm.
I've been breathing pure physics for over 45 years now, so it's something that animates me.
Mm-hmm.
Tell me a bit about. I was really struck by the fact that you're deploying machine learning, artificial intelligence, as it were, to find intelligence elsewhere.
Yeah, I mean, the reason for that is because the amount of data we generate
Right.
and the amount of time of signals that we have to search is just so enormous that it is impossible for us humans to basically sit down and visually go through all that. So to give you an example of our recent paper, I think which probably,
I
uh,
read it. Yeah.
yeah, you must have kind of gone through. That is a latest attempt in order to eliminate as much of what we call a false positive as possible using an automated technique before a human needs to intervene. So we had a set of something like 20 million different hits. What we call hits are the potential signal that our algorithm has detected. Now, if you ask a human to sit and go through this 20 million hits, it's impossible. It's not going to happen. But a machine can do it pretty quickly. A trained machine can do it very efficiently and very quickly. So this is what the attempt that we are trying to make. This is the stride that we are making in the field of SETI, that we have now tools available to us which were not available to us a decade ago.
Right.
These are the new tools that allow us to search terabytes of data in a very short amount of time, go through millions of candidates in a very short amount of time, and really push the limit of our understanding and our searches, so that we are not constrained by the computation anymore. We in the previous past, the SETI has always been constrained by how much computation is available to us, because the kind of signal that you want to search, the number of frequency channels that you want to search is so enormous that most of the searches that has happened earlier were only focused on a very particular set of signals, very particular range of frequencies, just because of the limitation in computation that was available to it. Now, due to the machine learning and AI coming into sort of play, we can expand that parameter space. That has never been that has never happened in the field of SETI. That's why I'm more hopeful, because
I see.
over the past 50, 60 years, whatever we have been doing, it is just probably you can consider it as a drop in a bucket of amount of thing that we are able to do right now. So I'm quite hopeful that with the help of AI and machine learning, we will be able to kind of survey millions of stars, be able to search millions of different kinds of signal, and that can really help us answer this question about existence of any kind of artificial signals that we are interested in order to find any signs of life out there.
Right. From 2017, onward, SETI had used classical techniques to sift through about 150 terabytes of data from 820 nearby stars. Now you're looking at a million stars.
Yeah.
I'm very interested to know the difference between the classical techniques that you used to deploy and now machine learning.
Right.
I'll come to the algorithms in a bit, but if you can differentiate for our viewers between
Right.
the two.
So traditionally, what we've been trying to do is use a single dish. So if you use, if you know what a radio antenna is, it's similar to like what people have on their terrace. For example, you have a dish TV. It's a dish. It's going to kind of look at a radio signal coming from a satellite. Similarly, we have an antenna, obviously much bigger in size, is 100 meter in diameter, so much more bigger than typical dish antennas people have. But the idea is still same, that there are radio sources out there. There are sources that could emit radio emission. So there are lots of astrophysical phenomena that's out there that for which we study. But along with that, we also have a hypothesis that if the ETI do truly exist, radio frequency is the most convenient way of communication compared to all the other ways that we had known so far. Obviously, there could be some medium through which we don't know, but through our current knowledge, radio is the best way through which you can communicate across large interstellar distances. So we hope that if there are truly ETIs out there, they might be using radio like we do to communicate across large distances. So we have to search each and every star in order to reject this hypothesis that there is no alien out there. There are no alien which are emitting this radio emission that we can detect or we can basically identify. So how do we do that? So we use single dishes in historically, which points towards a given star, and it looks at the star for a few minutes. Actually, typically with breakthrough listen program, we look at a even star for 5 minutes in 3 different cadences. So we go on and off 3 times in order to verify whether whatever we find is truly coming from the direction of the sky that star is located. Because there are lots of other interferences that are also goes into the radio antenna, not just the signal that we are looking in the sky. So radio antenna, when it is looking towards one patch of the sky, it has some sensitivity to everything around it as well. So if there is a car passing by, if somebody is using a mobile phone, if there's a Wi-Fi transmitter somewhere, all that will go into the radio antenna. This is what we call radio frequency interference.
Right.
So when the radio frequency interference goes into the data, we have to find clever ways to eliminate that radio frequency interference. And one of the ways by we do is on and off flipping. But that has a limitation, because you are basically wasting basically using 30 minutes of time to look at just one star.
Okay.
But now what we have is that we have multiple antennas, but they are not as 100 meter as big. They are smaller in size. So what we do is that we can digitally beamform, so that antenna can look at a much bigger area of the sky. So in that area, you have thousands of stars. So we can digitally look at individual stars, and then we can look at 64 different stars. So I can tell you how we can go to the million stars. So when we look at different parts of the sky, we can basically look at 64 stars at the same time. So now we don't have to do on and off, because we are looking at 64 stars. So what you can do is that you can compare anything that you find from a given star with everything else. And in that way, you can reduce the amount of time that you have to basically look at a given star in order to eliminate false positives. So through this technique, we can actually achieve million star target. And this is what we are doing with 2 telescopes right now. One is in South Africa called the Meerkat, and then there is a VLA, which is in the US. So we are using these 2 telescopes. VLA project is part of the SETI Institute, and Meerkat is part of the Breakthrough Listen program. But the technique is ideal, that we digitally beamform, and then these digital beamform actually looks at an individual star, and then we search the signal in real time. In most of the traditional way, we used to record the data, and then we used to search the data. But now we can do this in real time. And for that, again, artificial intelligence and machine learning is very helpful for us. Although we haven't yet deployed it, but this is our goal. That this paper that recently came out is a step in that direction. that in future we are going to deploy this technique that we have demonstrated on real data analysis. So the data, as soon as it comes in, we will be able to analyze it as quickly as we can, and then we will have the answer to this question: is there anything interesting in that part of the sky? And
Right.
this is how we will be able to go to the 1 million star.
Okay. Who's designing the algorithms as part of this machine learning? And part of the question is, how is the signal to noise ratio built into them?
So if you answer the question who, I mean, it's a team, basically.
Okay.
This one particular paper that we talked about comes through actually Peter Ma. He was an undergrad. He was a high school student when he started working with us. I
I
mean, you
see.
can't imagine what a high school student nowadays is capable of doing. Like when I was in high school, I didn't even know like many things as today's high school students do. But so he was a high school student when he started basically working with us. So we were chatting with him over the last couple of years. We've been sort of explaining the procedure, and he's pretty good with computing. So he was able to understand the problem that we were having, and he was able to come up with a solution which was quite efficient. So he came to us and said that, okay, this is how we will be able to solve it. And we asked him to demonstrate it, and he did demonstrate it. And then we were able to we were able to search these thousands of
I
stars, and
see.
that's how we wrote the paper. I'm sorry, what was your second question?
Now, the second question is about the signal to noise ratio.
Ah,
How does the algorithm
uh-huh.
determine that?
So there are two algorithms, like one which we call the traditional algorithm. So what the traditional algorithm does is that it takes an average of the data for a certain amount of time or frequency, and then it has a certain standard deviation built into it. So if you look at what we call a spectrogram, so if you look at a spectrogram, if you look at, like, for example, like 1,000 channels of a spectrogram, you can determine what is the standard deviation of a given particular frequency channel is. Um, Once you have that, if any particular frequency channel is above, let's say, 25 times the standard deviation of the spectrogram, we call that an interesting signal.
I
So
see.
that is the way we do it in a traditional way. Now, with the machine learning, we don't have to really do it in that sense, because for machines, we are trying to identify things which are in two-dimensional. So in some sense, it is still similar, like signal to noise ratio, that there is some signal which is sort of riding on top of the noise, but you can also change the signal to noise ratio. For the
I see.
training that we have done in this case, in that training, we chose the signal to we particularly not we didn't play too much with the signal to noise ratio, because we knew that the algorithm will probably going to take care of it.
Okay.
So
Interesting. Yeah.
yeah, so in case of 2D, because this is a different kind of algorithm, this is, in case of the traditional way, we are trying to identify frequency channels which are above certain threshold. In this case, we are identifying things in two-dimensional space.
Okay.
Concept is still same. We are also looking at the signal to noise ratio in this case as well, but this is slightly different than the traditional way we were looking.
Oh, how do you potentially recognize an ETI techno signature, considering we really don't know what we are looking for?
Yeah,
Uh,
that's a very sort of a big challenge for us.
okay.
So this is why what we call a kind of a typical signal that we search. So there are various different kinds of signal that we actually search for. In this paper, we focus on this one particular class of signal called signal which are extremely narrowband signal.
Right.
So almost all the natural occurring signal that we know, they're all broadband. So if we find a signal which is extremely narrow in frequency, occupy like few hertz of frequency channel,
Right.
that is definitely artificial.
I
So this
see.
is, yeah. So there is no natural process that we know can generate a few hertz wide signal. So this is the
Okay.
one way. But the major challenge is in identifying is not in actually identifying the signal, is in finding if the signal is truly sky localized.
I see.
because
Yeah.
because the kind of signal we generate are also narrowband.
Exactly. Yeah.
So our challenge is to not just find it, but to kind of identify whether the signal is actually truly coming from this one particular point in the sky.
Okay.
And for that, we use various different ways to eliminate, like what I said about earlier, talked about this on and off thing. Like we flip between two different stars, or we look at like multiple stars at the same time, because we don't really expect that all the stars will be emitting the same kind of signal. So if you see something similar, across multiple stars, that is definitely RFI or interference.
Right.
If you
Right.
see a signal only coming from one star, that is a true signal.
Okay. Slightly at a tangent, don't you think the James Webb Space Telescope could have helped in terms of getting rid of the kind of interference you might get on Earth, and then it could have transmitted to you? I don't know if it's a naive question or if there is some substance to that.
So JWST operates at a completely different wavelength. It's an
I see.
infrared telescope.
Right.
What we use is a radio telescope. So the frequencies are basically significantly different. There
Okay.
are different usage of JWST for finding a life, and I think one of the missions for JWST is also to look at the biosignatures. Although it is not sensitive to detect the kind of signal that we would hope the biosignatures might be to from not too far away star, like only for a few nearby stars you can do this. But the concept is still same, is to find the answer to this question, like, are we alone in the universe? So JWST, what it can detect is these biomolecules in the
Right.
atmosphere of these extrasolar planets through this transit technique. So when a planet passes in front of a star, a fraction of the light of the star gets absorbed by the atmosphere of the planet, and that absorption can be detected if you have a sensitive enough telescope like JWST. So you can detect a particular line that can only be there if there is a biological activity. That is what we call a biosignature.
Right.
So JWST can detect them for few tens of light years distances. But the kind of signal we look for is what we call techno signature, because these are evidence of technologically advanced
Advanced
life.
civilization. Right.
Yeah. So for us, we don't really care if they are I mean, if they could be robots for our practical
Oh,
purposes.
yeah.
Yeah, for us that doesn't really matter. As long as they have the technology to produce radio waves, we are fine. We don't really. It doesn't really matter to us that what kind of biology the life will have.
Right.
So that actually allows us to search much further out, because our kind of signal we search for can be detected across all the way to the other end of the galaxy. So the radio signal, as I said, because this is the best way through which you can communicate across interstellar distances. So you can produce radio waves which are so powerful now with our current technology itself, which can be detected across all the way to the other end of the galaxy. So it's not that hard for any
Right.
advanced civilization residing in our Milky Way to produce a powerful radio transmitter which can be detected across everybody else in the galaxy.
Right.
So yeah.
It would be interesting if the James Webb produces a signal which is indicative of at least life
Yes.
in some place, not necessarily a technologically advanced civilization that would communicate with SETI.
Yeah.
So they might trump you in that sense, that we found life before you
Yeah.
did, but it's not smart enough for to talk to us.
I no, I will totally be excited if that happens. I mean, this is going to be a fascinating discovery
Yeah.
either way. If you find even a sign of a biological activity on an extrasolar planet,
Right.
that's the biggest discovery in science. Like, we
Indeed.
found that life is not unique to Earth.
Right.
It's possible that similar life can grow outside and can exist outside. That's even bigger motivation for us to look out for technological advance. Like, because if with JWST, if you're able to find life which is such a in a solar neighborhood, think about the entire galaxy. I
Right.
mean, if you have just our nearby planet hosting a life, that means that there are thousands of light years away. There could be extremely advanced civilizations out there which have the technology that we can detect sitting here.
Right. Right.
So if I wouldn't be disappointed by that. I feel like that would be a biggest discovery, and that will give us even more motivation to. And
To
I
look for
think,
advance. Right. Indeed.
yeah,
That's
yeah,
true.
yeah, and I think there will can also benefit in terms of us getting some more funding because SETI has always struggled to get funding,
Yeah.
because it is always considered as the likelihood of success depends on the chance. Like,
And
you
it's
have
an
the
outlier science even now to look
right,
for.
exactly.
Yeah. Yeah.
But if a JWST does make a detection, that would be a biggest
Change
thing. And
everything. Yes. Yeah.
yeah, yeah, that then what we are doing is just an extension of that. Like, it's
Absolutely.
Right.
Absolutely. Another just last couple of things. One question that's always preoccupied me when it comes to issues like this is the enormous distances that we are talking about in terms of communication. Say, for the
Mhm.
sake of argument, you're looking at Proxima B,
Uh-huh.
which revolves around the Proxima Centauri red dwarf star, about 4.3 light years away, which is roughly 40 trillion kilometers from us.
Mhm.
It takes about 4 years, 3 months, something one way. So you're still, even at the nearest distance, you're still looking at an 8 year two-way traffic.
Right.
In the life of a scientist,
Yeah.
as a scientist, how do you retain your enthusiasm for such long durations?
Right. So SETI is not two-way sort of communication. So we are
Right,
not
right.
we are not purposefully transmitting any messages
Indeed.
so
Yeah,
far. So far,
yeah.
what we are hoping for is that there are intelligent, advanced life, extraterrestrial life out there, which are producing radio waves, which is passing through us right now. Now, it can happen that we may be completely missing them because they might have existed like billion years ahead of us. So their signal have already passed through us, and they might have been destroyed by now. So the signals no longer exist in the galaxy, so we can't see them. But it can also happen that they could be a few that there could be a star which is like 1,000 light year away from us, and their advanced civilization may be like 1,000 year ahead of us, or few thousand years ahead of us. And 1,000 year ago, they transmitted something which reached us right now, and
Just
we are
now, yeah.
searching. Yeah. So in SETI, if you know about this thing called a Drake equation.
I
So
do.
in the
Yeah.
Drake equation, we have these various different probability parameters, and the last one is the most important one. Is called L. Is the lifetime of the signal that we expect to find. If the signal lasts for a few hundred years, the chances of detecting it will be very less. But if it lasts for like a few thousand years,
I see.
then the chances of detecting it will be very high. So for us, the main constraint is not so much as the distance, it's the lifetime of a signal. So even if the signal is like coming from a far away, but if they last long enough for us to overlap within our search range, then we can find it. But if it
Right.
lasts for only like a few tens of years, then we have no hope of finding it. So you
Absolutely.
can,
Yeah.
so that's something that is a definitely a very important factor for us.
Right. As a scientist, what would constitute to you an intelligent techno signature? And when you find it personally,
Hmm.
how would you internalize it? I know the second one is a speculative question, but I'm just trying to get into the mind when you
Right.
find something of this scale.
So we have actually designed an entire protocol in order to assess any kind of detection, because this is something we have thought about, like what would do if we find something. So there are various different steps that we have basically the SETI community has agreed upon, which we will follow. Like for example, if through my project, through my particular observation, I do make a detection, I find something that is extraordinary, which I
Mhm.
can't explain through any kind of natural processes. I can't really eliminate as interference. It is truly coming from this one particular part of the sky, and it has no other way of explanation for it. Then there are other ways through which you can verify it. You basically allow a completely different team to look at the same part of the sky with their own different telescope, with their own different tools, and ask them to reproduce it. So this is a validation. So so this is just an example I'm giving you, but
Right,
there are
right.
various different steps. After if it happens that if that's a truly a consistent persistent signal in the sky, and after all the different cross and checks that we can think about, we cannot really rule it out. That would definitely be a major or a significant discovery. And we have a mechanism about how do we basically report it. We
Okay.
don't really, I mean, it's completely different than what people think about, like SETI people. Like we don't really go to the press. We don't have a red phone in our office to call the
Well, there
president.
are no breaking news banners on a television channel, isn't
Yeah,
there?
yeah, yeah. So we don't have a red phone in our office to call the president saying that, hey, we found something. Uh, the best way for us to do would be to write a scientific paper on it, and publish it, and let it go through a reviewing process. So there are people who are not from the SETI community, for example, who are probably may have more understanding about radio antennas, radio signals, and like, so they could also validate us. They could also help us eliminate any other possible things that we might not have think about. So one of
Right.
the ways that we will be able to write a paper, and if after thorough reviewing, if the reviewing goes through multiple referees and all of them agrees and cannot find anything wrong with it, that we can publish. Once it is published, then it's in the public
Right.
domain.
Right. Right.
So it's a similar to like every other discovery I can think about.
Right. Right.
The significance of it is massive. It's not as same as like finding a pulsar, for example, or finding a fast radio burst. It's certainly one of the most biggest discovery a human has ever made, if we do find it. And yeah, we will deal with it as it comes.
Yeah.
So far, we have made only our plan till we publish it, and then
Right.
obviously the media
Yeah.
will definitely take over. That you can't control anyway. That's
Yeah.
something is out of your control.
Before I let you go, I'm sure there are universal frequencies that you believe that any intelligent civilization would use to communicate.
Right.
Is that one frequency, or there are several frequencies like that?
So there are several different frequencies that people
Okay.
have basically suggested over the years. Now, first of all, we have absolutely no idea whether that will be universally true. Now, one of the frequency which people have speculated is the frequency of hydrogen. Now, hydrogen is one of
Okay.
the most common element in the universe. Everything basically is the first building block of everything. Like you have just one proton and one electron. That's just basically makes the hydrogen. So you have hydrogen is in abundance. So anywhere, if there is an advanced civilization, they know about hydrogen. So hydrogen has a very particular frequency at 1.4 gigahertz. So if you do find, if you want to communicate across interstellar distances, if you send a signal at that frequency, you can be sure that they will have antennas and they will have instrument to detect this frequency. If you send it to a completely random frequency, the chances are that the other person will miss it, because you don't necessarily build an antenna or not build your instrument to detect that frequency. But hydrogen is so common that any radio astronomer, any ET radio astronomer would know about it. So they have
Right.
instrument to build, they have instrument to search for it. And if you send a signal to at that frequency, then you would detect it. Now, this is what obviously people have suggested, but there are other frequency, like for
Oh,
example, multiples of pi's, or like pi multiply with hydrogen, and there are other ways,
okay.
frequencies you can think
Okay.
about. There is also, people have speculated what we call a water hall. Like for example, in case of like if there is a desert, and in the desert you have a small a place where you have small
Yeah.
water hole, like all the animals will gather there to drink. So the frequency of hydrogen is H. The water is H2O. So it's
Right. Right.
hydrogen and OH. So the frequency of hydrogen is 1.4 and frequency of OH is 1.6. So you can look at this 1.4 to
Interesting.
1.6 frequency. It's called a and sort of extraterrestrial water hole, like similar
Oh,
to
I see.
us. But it is an hypothesis. Obviously, ETI doesn't really care about it. That is completely. But
This
just
is
for
remarkable. This is
yeah,
remarkable. On
but
that fascinating note, Dr. Gajjar, I know you have other things to do. Let's just hope that the young man from Botad becomes the first one to at least see some intelligent ETI communicating with us.
I hope so too. And thank you so much for taking time and having the discussion. It was very